Okay, thanks very much. And thank you to everyone in the group. There was a extraordinary variety and diversity of opinions, which I will make no attempt to reconcile, but rather just report as is, so apologies in advance if I editorialize or even misconstrue your point. So I think the one foundational question we faced was like, well, first of all, like, is this always the appropriate tool for the job, information theory? Especially, thanks. Especially in scenarios where it's difficult to identify a sender and a receiver or a channel, or you might have multiple channels at multiple scales. So, for example, one common situation you'll face is that you might have a cellular timescale, but also an evolutionary timescale, and it's not clear how these should be sequenced. Right? It's also not clear how to deal with this tension between finite and infinite data. Then this shows up in several cases. Sometimes you have for example, a DNA binding protein that just has to bind to 6 sites, right? And so in that case, it's not clear what the difference is between a sample and the full data set itself is. And sometimes your transmitter might be absent entirely. I think the second theme that we identified was the need to address the fact that biology exists on multiple scales, right? So there's a question of how you coarse grain systems in a systematic way or in a principled way, right? So biological information doesn't average out nicely or cleanly all the time in the way that it does typically in physics, and you have information from smaller time scales or length scales that bubbles up and affects the entire bulk coarse grained behavior of the system. And it's not clear how to deal with this. So there are a few sort of mathematical methods developed to address like very obvious foundational problems, like how do you even measure entropy in the first place? So I think like typically we take it for granted that if you have a random variable, it's straightforward to measure its entropy, and this is actually not the case. There's a kind of cottage industry of entropy estimators going back to the 50s with Bashar and Miller to try to address small sample effects. This works out sometimes. If you have a large cardinality random variable and you don't have a very large sample, it can be very difficult. And so this is like work on this is still ongoing. I don't think the problem has been completely solved yet, right? So if you can't measure mutual information between your sender and receiver, then it's not clear how much further you're going to get. Right, and also like there's another cottage industry of different entropies that have been developed, right? And like these are related to each other in some way, right? Shannon entropy, Renyi entropy, etc. KL divergence, and it seems like the theory is behind the practice here. Okay, so moving right along. If you're more comfortable with dynamical systems or control theory or estimation theory, sometimes the relationships between these fields in information theory is unclear. And lastly, in terms of the tools that are already available, would like to make one pitch here for just like general standards of software engineering. There are a lot of tools and methodologies for developing robust, reliable software that actually I don't think that junior scientists learn in academia. And if you want your tools to have impact, shameless plug for Tom's sequence logos here. There's actually a lot to learn, and it's sort of like it's a Pareto improvement, right? It makes your software more reliable and easier for others to use, and that increases your citation counts. So with that, let me just stop here and thank my group again, and thank you all.